In today's section, we will be doing section 9.3, which is about graphing rational functions. We will graph rational functions using the asymptotes and points of discontinuity. We talked about asymptotes when we dealt with hyperbolas. An asymptote is a guideline. We'll be using guidelines. Okay, a point of discontinuity will be pretty new to us, though, in this section. We're going to be looking at mostly vertical asymptotes. I'm going to give you some ideas about horizontal asymptotes as well. Graphing rational functions, first we need to find out whether the graph will have a vertical asymptote or a point of discontinuity. And we'll have one or the two. When you're looking for these things, you're looking at the denominator, okay? And you're thinking about the domain. Any value of the domain that would make the denominator of the function equal 0 will be a vertical asymptote. Again, domain is your x values. You're looking at your inputs. So if there's any input that you can put into the function and the denominator would equal to 0, that is going to imply a vertical asymptote. So looking at this expression, very simple expression. You're looking at it's x over x plus 3. Thinking about the domain, what values of x can you have? Or what can't you have? That denominator cannot equal 0. So when x equals 3, the denominator is 3. So that means x equals 3 is a vertical asymptote. And that's what you see drawn right here. So now that is a vertical guide. Okay? The graph will not cross over that line. So it divides the graph into two parts. You have the parts that is to the left of the asymptote and a part that is to the right of the asymptote. And what I've made, okay, I've made two tables. Okay, one for what is going on with this graph to the right of the asymptote, and for one that is going on, saying what is going on to the left of the asymptote. So basically all I've done is chosen some values. I chose -4. I inputted it in for x. Okay, you get -4 over -4 plus 3, which is -4 over -1, which gets you the 4. When you input -5, you get out 2.5. When you input -6, you get out 2. When you put in -7, you start getting fractions, 7/4, which is about 1.75. Okay, when you put in -8, you get 8/5, which is about 1.6. Okay. On the other side, you're inputting these values. So I inputted -2. I got -2. I inputted -1. I got -1/2. I inputted 0. I got 0. I inputted 1. I got 1/4. I inputted 2. Got 2/5. Okay, so you can see that those values are increasing, but not by that much. Okay, as you're making each table of values, you think about what the y values are approaching as you're moving to the right and to the left. Okay. This may be helpful to graph as you go. As you're getting these values to the left, input -4,4. Input -5, -2.5. Sorry. Input -6,2. Input -7, 7/4. Okay, which is about there. Input -8, 8/5, which is about there. What are they getting close to? What are they never going to cross over? There also is a horizontal asymptote, and we're going to talk about that in a moment. Okay, on the other side, we can input -2, -2. We can input -1, 1/2, or -1/2. We can input 0, 0. We can input 1 and 1/4. We can input 2 and 2/5. Okay, if we want to continue on, we can go on. Okay, what's happening as it gets close to the asymptote? It's following that asymptote in that direction. You can see the direction of the graph by the points. It is getting close to that and never crossing over that asymptote. So same thing here. It's getting close to that, never crossing over the asymptote. Now, in terms of horizontal asymptote, what are these numbers approaching? Okay, if you look at the first terms of each, the numerator and the denominator, if they are the same degree, what you can do is basically take the coefficients and divide them. The coefficients are 1, meaning that you have a horizontal asymptote at 1. Okay, notice that these values are never going to cross over y equals 1. Okay, as you keep inputting values in for x to the right, 3, 4, 5, 6, 7, okay, the numerator will never be as large as the denominator. As you keep going to the left and inputting -9, -10, -11, these numbers will reduce, the y values will reduce, but they're never going to get to 1. They will never get to 1. Okay. All right, on this, we're going to graph this expression, some things that you know. Okay, it has a vertical asymptote. What's going to make the denominator equal to 0? Okay, x cannot equal 6. That is a vertical asymptote. Looking at the coefficients, there is no x term. There are 0 x's in the numerator. Okay, so what is 0 over 1? 0. This should probably have a horizontal asymptote at 0. That will help you graph this function. So did you get this? Okay, notice my features of my graph. I have the vertical asymptote at 6, and I have a horizontal asymptote at 0, just like stated before. The rest is making a table. What's going on to the left? What's going on to the right? You should take some time, pause the video, and make sure you can come up with this graph. Okay, so what is a point of discontinuity? If a part of the denominator can be factored out, then the number in the domain that would have made the denominator equal 0 is no longer an asymptote, but it's now a point of discontinuity. Okay, the graph is able to have both a vertical asymptote and a point of discontinuity at the same time. It's going to be best to see some examples with this. Okay, here's our first example. Notice that both the numerator and the denominator are factorable. Okay, we want to do that. Okay, we're going to factor both parts. Okay, what you notice in the denominator now is that x cannot equal 5 and x cannot equal 1. Okay, if we saw this problem 2 minutes ago, we would have said this has 2 vertical asymptotes, so we would have divided the graph into 3 categories. But what you should notice is the x minus 1's cancel out. When that happens, the x equals 5 is still a vertical asymptote. But the x minus 1's that cancel it out, where x is 1, it is called a point of discontinuity. It is a point where the graph jumps, basically. We are going to use this to graph our expression. And notice, even if we left it here, okay, with the coefficients of 1, or we come down here with the coefficients of 1, both of them are telling us that we have a horizontal asymptote at 1. So now let's go ahead and give this a graph. Okay? Again, remembering we have a vertical asymptote at 5, and we have a point of discontinuity where x is equal to 1. Okay? That was our work again. Okay, and again, you'll see it drawn a little bit better, but we have our vertical asymptote at 5. And you got to remember, okay, where x is equal to 1, okay, something's going on there. That's our point of discontinuity. Okay. Oh, what else I forgot? Okay, is we should have a horizontal asymptote at 1. So now, I have what's going on to the left here. Okay, what's going on to the left is I input 4, I get a -5 output. I input 3, okay, I get a -2 output. I input 2, I get a -1 output. Look at this. When I input 1, wait a second, we can't input 1. That is a point of discontinuity. That point doesn't exist. Okay, and I'll show you how we can graph that. Input 0, get -1/5. So as I input these points, okay, I get 4, -5. That's a little bit off our graph right now. I got 3, -2. That I can put on there. 3, -2 is right there. Okay, I get 2, -1. That point was right there. 1 doesn't exist, so I skip it and go to 0, -1/5, which is approaching that 0, but not quite getting there. Okay. So what's going to happen is this is going to rise up from here along following the asymptote, and it is going to rise, okay, getting close, very slowly getting close to 1. But again, this doesn't exist at 1. So look at this. I'm going to erase that point, and as it gets to where x is equal to 1, we skip over that point. We put an open circle. That is our point of discontinuity. On the other side, I don't have to worry about a point of discontinuity, so I can just input these points and graph those points accordingly. So our graph looks like this. There's our point of discontinuity. Okay, again, look at our horizontal asymptote. Okay, approaching 1. Look at our vertical asymptote there. I want you to try to graph this. Remember to factor the numerator and denominator. Find the values of x that cannot happen, that will make the denominator equal to 0. determine if they are vertical asymptote, or determine if they factor with the numerator and make a point of discontinuity, okay? And then graph accordingly. Your graph should look like this. Again, notice point of discontinuity where x is equal to -2. Vertical asymptote where x is equal to -3. We will go over this graph in more detail tomorrow. This is a second graph that I would like you to try. Give it a moment, pause the video, and give it a try. Okay, let's go over this together now. And what I'm looking at here is that x cannot equal 2. And I'm not sure if that's a vertical asymptote now or a point of discontinuity, but I know that x equals 2 cannot happen. If I look at the numerator now, it's being observant now. Looking at the numerator factors. And it does factor with the denominator. It factors completely. Okay, and when I do that now, I'm just left with this expression, which is a linear expression. But we got to remember, x cannot equal 2. Is that a vertical asymptote? No, it canceled out. It canceled out. So that is a point of discontinuity. So in terms of this graph, what we're going to do is graph this as a linear equation with a y-intercept of 2 and a slope of 1. And we're going to remember that this does not exist at 2. We have a point of discontinuity at 2. So I'm going to first go ahead and draw my line so I can draw it with some accuracy, and then go back and put in my point of discontinuity where x equals 2. X equals 2 right there. There's my point of discontinuity. This is the graph of this rational expression. I also want you to try this one, thinking about vertical asymptote and horizontal asymptote. Where are they? Use those as guides to help you graph them. And we will go over this one in class tomorrow.